Okay, today's lecture 16, and the topic today is continuity, very closely related to limits. In fact, it's hard to talk about limits without also soon thereafter following it up with continuity. You see how deeply they're tied together as we explore continuity. Continuity could be as simple as this kind of question: can I draw the graph of this function without lifting my pencil from the paper? And if the answer to that is that you can, then more than likely that's a continuous function. Unfortunately, continuity is checked at individual x values. So it seems like almost an impossible task. How do you decide which x values to test for continuity, especially if the function is defined over all reals? So what you do is you only check continuity at values at which the function itself is suspect. If you have a sneaky feeling that it might be discontinuous at 3, then you probably want to check for continuity at x equals 3. Now this definition for continuous that you see here, and there's a lot of these points, and these are taken right from the textbook, we'll actually do this process, but we'll probably do it in 3 pieces. I think it makes a little more sense to do it in 3 pieces. But a function f is continuous at a number, so we check it at individual x values, if the limit of the function as x approaches a is exactly the same as the f of a. Now if that happens, that seems a little almost mundane, a little too simplistic, but if that happens, then a function is in fact continuous at that value. Now, in practice, what is this going to look like? So we're going to check for continuity at an individual x value. So we'll check it at a value that possibly there's division by 0 at x equals 3. So then we want to check it at x equals 3. Or we might check it at a value that the authors give us to check it. So the first thing we'll check is, does the f of a exist? Okay, the f of a exists. Now, another way to ask that question to yourself is there a point plotted there? If there is not a point plotted there, end of discussion, it's discontinuous. Okay? So is there a point plotted there? So if in fact there is a point, a comma f of a, then it passes test 1 of continuity. Then we go on to test 2. Let me see if I can spell exists right this time. So does the limit exist on this function as x approaches a from both sides? We want to come in from both directions. So does it have a limit at x equals a, or x approaching a? Again, if it fails there, end of discussion, it's discontinuous. So if it fails part 1 or part 2, then it's over. It's discontinuous at that point. Now, these two together, then we'll take our answer to part 1 and our answer to part 2, and in effect, if they're the same, if the answer to part 2, the limit as x approaches a, if in fact it is the f of a, then it is continuous. And in fact, that's what the definition in your text says. But I like to look at it in 2 pieces before we get to that point, and that way it can fail earlier in the problem. If it doesn't have an f of a, it's over. If it doesn't have a limit from both sides, it's over, and then we don't have to go on to this third piece. So if it passes all three pieces of this continuity test, then it is a continuous function. So let's look at some that are in fact failing in part 1 or part 2, or some of them that actually get by part 1 and part 2, but they fail in test number 3 here. So let me draw a picture. And let's say that we have a graph that has a hole in it. Comes up here to a point. There's another point right above it. So I'm trying to get several different things that might happen in a function all on the same picture. We'll look at some algebraic interpretations of this as well, but just a graphical or geometric approach. Let's say that this is A, and this y value is capital L. Say that this is C, this is B. Let's say that this is M. This is capital R. This is S. What else do I need here? I need this. So I've got lots of x values here that I want to examine. I want us to know what's going on at A, and then later at B, and then later at C. And then the M and L and Q and R and S, those are just corresponding y values that we'll need as we progress. Let's see if this is continuous. Continuous at x equals A. What do you think? In fact, let's just lay out here on the table what we think is going to happen. Do you think it's continuous at A? It's not continuous at A. Now I could get cute and come down here and draw this and make this circle and do that, right? I never did lift my pen from the paper, but we're not talking about getting cute like that. Clearly there's a gap there, right? The little open circle is just a way we represent that. Actually, there's literally a gap in the two pieces of the graph. So it's not continuous at A. Do you think it's continuous at B? Is that a continuous function at x equals B? Not continuous there either. It's broken. It's got two different pieces. You think it's continuous at C? It's not continuous at C either. But we've got a different reason why they're discontinuous. So let's take at x equals A. So does the f of A exist? Is there a point plotted at x equals A? No. Therefore, what's our answer? Discontinuous. Okay? Discontinuous. Continuous at x equals B. Well, we've already decided that it's not, but let's see how this test goes. Does the f of B exist? Is there a point plotted at x equals B?
Mm-hmm.
Yes.
And what is that? B what?
R.
R? So that tells us to go on to part 2. Does the limit exist? As x is approaching B. So as we come into B from this side, and we come into B from this side, are we closing in on the same y value? No, doesn't have a limit. So the first one failed because there was not a point plotted there. no hope of being discontinuous. The second one, there was a point plotted there, but we were approaching different limits from each direction. Now the third one, let me keep this diagram here so we can refer to it. Is it continuous at x equals c? Again, we think it's not. Let's go through the test. Is there a point plotted at x equals c?
Yeah.
Yes, there is. What is that?
Yeah.
C, comma, m. Does the limit exist as we get closer and closer to c from both sides? Are we getting closer and closer and closer to the same y value? Yes, we are. What is that?
Q.
Q?
Q, yeah.
So is our answer to part 1, is the limit of the f of x as x approaches c, is that the same as the f of c? Is this value that we're approaching from both sides, is it the same as the point that got plotted? It is not. We're getting closer and closer and closer to q, but the point that got plotted was down underneath that at m. So is the limit q equal to the actual point that got plotted, m? No. Discontinuous. So it can actually make it to the, I mean, you can have an answer to part 1, you can have an answer to part 2, but unless they're the same, part 3, test 3 fails, it's discontinuous. Okay, but there's 3 different types of discontinuity. I think we've had graphs that had this situation before. This was just some kind of a function with a hole in it, right? A line with a hole in it, a parabola with a hole in it, whatever it is. It's just got a bad value in the domain. This would be an example of jump, what's called, the authors refer to as jump discontinuity. And then we also know graphs can be discontinuous because the graph goes to infinity. So I didn't have an example of that, but we've seen this time and time again, that it can have a vertical boundary, and the graph goes crazy as we get closer and closer and closer to whatever that vertical boundary is. So let's say this is A, this is the line x equals A, which is a vertical asymptote, and if we would check the limit, in fact, we wouldn't even make it this far, would we? There isn't even a point plotted there, right? So I don't even think we'd make it to part 2. It actually fails part 1 and part 2 here. There is no limit, so the limit does not exist. And in fact, part 1 of that also fails. There is not a point plotted there, so it cannot be continuous. So this is infinitely discontinuous. So the authors will refer to that, and I'll refer to it as infinite discontinuity. So continuity can be a very, very simple concept. Can you draw the graph without lifting the pencil from the paper? Or you can look at it in pieces like this. Is there a point plotted there? Do we approach the same limit from both sides? And are those two values the same? But whichever way you approach continuity, I don't think it needs to be a real complex process, if you look at it, especially in these 3 pieces. Some functions, you can't talk about coming in from the left and from the right both, because the function doesn't exist on both sides. So you'll see this second piece here, the second definition. A function f is continuous from the right if it has a right-hand limit, and is continuous from the left if it in fact has a left-hand limit. Now, a simple function for which that is true, let me just write it down here. Let's say we're talking about the square root of x function. Well, it doesn't exist on the other side of 0, right? So we really can't come in from the left of 0. We have to only come in from the right of 0. So when we're talking about a limit here, we can only come in from the right because it's only defined on positive values. So it doesn't make sense to judge this one the same way we judge the other one because we can't come in from both directions. So this would be continuous from the right because we can only come in on the right. So the graph of this looks something like that. It's a half parabola. And we would expect that we can only come in from values larger than 0 because the function doesn't exist on the other side of 0. So it's not because we're trying to be picky or choosy here. It's because we don't have any other choice. I mean, we're not saying, well, let's just do it from this half or this half. We don't have a choice. The function does not exist on the other side. Okay, and this third definition, continuous on an interval. So really continuity itself is defined at a point, at x equals a or x equals b or x equals 0, whatever that single value is. But for a function to be continuous on an interval, it must be continuous at every single x value in that interval. Although continuity itself is not defined per se over an interval, we can define what it means to be continuous on an interval based on the original definition of continuity, continuous at all points in that interval. And again, if we talk about an interval, let's say the function that I have up here above, if it's continuous on the interval from 0 to 1, it's understood that we don't have to look at it on the other side of 0. And we don't have to look at it, even though we could, on the other side of 1. If it's an implied one-sided limit, then we go ahead and make that implication. But for the most part, we check continuity at a single x value. This next page has a lot of real helpful, useful, valuable theorems on it. Things that we would really, really like to do, they give us the permission to do here. If f and g are two continuous functions at certain values, let's say a and c, then we can add them, they're still continuous. Subtract them, still continuous. So the sum of two continuous functions at a point at which they are continuous is also continuous. A constant times a function, the product of two functions, and in fact the quotient of two functions. This is really the only one that creates a little bit of grief sometimes, is that sometimes when we take functions that are in fact continuous at a value, that value happens to be 0 sometimes. And then we end up dividing by 0, so it gives us a new restriction. And it says that right here. If the g of a is 0, then we have to kind of delete that from the domain. But anything else, if they're added, that's fine. Subtracted, multiplied by a constant, any of that stuff is fine. If the individual functions are continuous, their sum, difference, product, quotient, all that is also continuous. Now that's not the big one. To me, the next one is the big one, which is the nice thing about polynomials. Polynomials are continuous everywhere. Boy, that's nice. And in fact, they're even more well-behaved than just continuous everywhere. They're what's called a smooth curve, so they don't have any corners, no cusps, no radical sharp changes in direction. Polynomials are very, very nice and easy to work with. And I could say something corny like polynomials are our friends for this reason, but I'm not going to be quite that corny today. But they are easy to work with. Now, not so easy, but yet not bad either, are rational functions. Rational functions are continuous everywhere that they exist. I know that sounds a little odd, that if they don't exist, they can't be continuous, but if a number is in the domain, what's called the natural domain of a rational function, it's continuous there. So rational functions are only discontinuous where the functions themselves don't exist. Well, that makes them kind of nice too. Not quite as nice as polynomials. But it is nice to know that that's true about rational functions. Let's look at a couple before we go on to this last one. We'll come back to this other theorem. Let's look at this function. It's a rational function. So let's go over what a rational function is. Again, a rational function is somebody want to tell me what that is? Okay, it's a fraction of two polynomials, okay? So the numerator is a polynomial, denominator is a polynomial. Now that doesn't mean their quotient is a polynomial. Sometimes it is. This one it is not. But it is a rational function. What's the domain of this rational function?
All reals except 3.
Okay, all reals except 3. 3 is a bad value. So 3 is not even in the domain, so it doesn't make sense for us to evaluate continuity at x equals 3. We know it's discontinuous there. How about all other values in the domain? Suppose we had this question. Or even, that becomes part of this question. Is it continuous? At x equals 2? Well, what do you think? Is it continuous at x equals 2? Didn't we just have a theorem that said all rational functions are continuous at all values in their domain? Well, 2's in the domain, right? The only restricted value is 3, so certainly this would have to be continuous. So what's that allow us to do? That allows us to go back here and say, well, what's wrong with just plugging in 2? There should be nothing wrong, right? We should be able to just put 2 into the function, and whatever we get at 2, we would certainly be approaching that as x approached 2. So the only suspect values of a rational function are the values that were deleted from the domain. What do you think about this? Is that a continuous function? Y equals sine of x. Can you draw the graph, a sine graph, without lifting your pencil from the paper?
Mm-hmm.
Yeah.
Continuous function, right?
Yeah.
How about cosine? Is that a continuous function? Can you think of a value that's suspect at all? Pi over 2, pi, 7 pi, 11 pi over 6. All of those have a corresponding y value. Those are both continuous. Now, does that mean that all trig functions are continuous?
Tangent.
Tangent doesn't. Can you give me a good reason why the tangent? Now, let me put this in here first. Isn't tangent the quotient of sine over cosine?
Mm-hmm.
Now, the sine's continuous. You just said that. We all agreed. Cosine is continuous. We all agreed on that. Why isn't the tangent continuous? It's the quotient of two continuous functions.
Asymptote.
But if a sine of x is 0.
Okay, because cosine does take on the value 0 sometimes, right? When is the cosine?
Pi halves.
Pi over 2 and 3 pi over
Okay, pi over 2, right? That was called out. Is the cosine 0 there? And if the cosine is 0, that would make the tangent undefined and therefore discontinuous. Somebody said another value. 3 pi over 2? How many values could we list there? How many
I mean-
times does the cosine take on the value 0? An infinite amount of times, right? I mean, isn't it just this nice little oscillatory function? Let's suppose we wanted to write them all.
Pi over 2 plus pi r, some k or something.
Okay? So how do we get from pi over 2 to 3 pi over 2? Don't we just add pi, right? Once you get one of the bad values, don't you just go pi from there? Right? Either left or right? Ought to work. So, have pi over 2 plus n multiples of pi, where n is an integer, and that ought to be all the places where the cosine is 0, therefore the tangent is undefined. Is that okay? Everybody convinced? Can you get a visual of the tangent function? It's undefined, right, at pi over 2? Tangent function looks something like, if this is pi over 2, right? That's our old friend there, the tangent function. Clearly discontinuous at pi over 2. Even though it's the quotient of two continuous functions, one of them takes on the value 0. Okay, here is the last guy on this page. The following types of functions are continuous at every number that is in their domains. Now keep that, that's a little kind of a qualifier there. They're not all continuous everywhere. Polynomials are. Rational functions are continuous at every number in the domain. Square root, cube root, trigonometric functions. Well, we just decided the tangent's not continuous at pi over 2, but pi over 2 is not in the domain because you can't find the tangent of pi over 2. Inverse trig, exponential functions, and logarithmic functions. Now that's a little bit deceptive because don't think that they have, none of these have any bad values. A lot of these have bad values. A lot of them have discontinuities, right? Rational functions have a lot of discontinuities, but not at values that are in their domain. I think I've got an example. Yes. Relative to this last theorem. So that's the function. So is that continuous at pi over 2? Are there any bad values for this function? No, the numerator's fine, right? The numerator, it doesn't matter if it's ever 0, that's not an issue. Are there any bad values for the denominator? You say, well, what about where the sign is 3? Wouldn't that be a problem? Tell me where the sine function is 3. It never is, right? Where is the sine function? Always. Between 1 and negative 1. So when would the sine function be 3? It never is. So we know the sine to be somewhere between 1 and negative 1. An unaltered sine. It hasn't had its amplitude changed. So are there any bad values for this function? Absolutely not, right? So would we expect it to be continuous at pi over 2? Yeah, it should be continuous everywhere. There's no deletions from the domain at all. So we don't have to worry about it if, in fact, there are no deletions from the domain. It's continuous everywhere. Let's see, where are we headed here? Theorem 8, these are in the text. Function, if f is continuous at b, and the limit of g of x is b as x approaches a, then the f of the g of x is the f of b. Now that last line might phrase this a little better. The limit of a composed function, apparently what are we able to do with that limit? Kind of slide it over the function f and slide it into the inside function, take the limit of the g of x, and then take that result, plug it into the f. So in the words of your authors, the limit symbol can be moved through a function symbol as long as the function itself is continuous. Okay? So we can take this limit and then just analyze what's going on inside there, do our limit thing, get an answer, take that answer, plug it into the function. That's legal, if in fact the function is continuous. Theorem 9. How is Theorem 9 a little different? If g is continuous at a, and f is continuous at the g of a, then the composite function, f of the g, given by the f of the g of x, it is also continuous at a. So let's try to put that in words. Composition of a pair of continuous functions is also continuous. Right? Does that seem to answer that one? Let me see if I have your author's words written down here. Yeah, that's what it says. Okay. Continuous function of a continuous function is also a continuous function. Right? We've got a composition of continuous functions. It itself is continuous. Okay, this is kind of an interesting little theorem. And it kind of falls out based on continuity. If, in fact, we have a continuous function, and we examine a piece of that continuous function, and it's connected from some initial point to some terminal point, then we know for a fact that the function, the y value, takes on every value between my two thumbs. Every intermediate value. Because there's no way I can connect this dot to this dot and be continuous without taking on every y value between here and here. Right? That's what the intermediate value theorem says. Suppose that f is continuous on a closed interval, so from some starting point to some terminal point. Let n, capital N, be any number between f of a and f of b. Then there exists a number, now a meaning at least one. Sometimes it actually says that. There is at least one number, c, somewhere between a and b, such that the f of c takes on this value. So the picture that goes along with this intermediate value theorem is, let's take a and let's say this is f of a. And then we've got some other point up here. Let's say that is b. So we've got these 2 points, a, f of a. And b, f of b. And it says the function has to be continuous on this closed interval. So there's no gaps, no jumps, no discontinuities of any kind. So let's say it does this, okay? I have to connect those 2 points. And I pick out a value somewhere between f of A and f of B. Let's say that n is somewhere between f of A and f of B. I don't care where we pick it. Let's say it's right here, capital N. Now, is there some x value between A and B where I plug that x value into the function and it takes on the value n? Yeah, there has to be. It's continuous. So what do? I come over here to the function. There it is. There's that value c, such that when I plug c into this function, what does it give me? It gives me n. Now, it says there's at least one. There is a value. Sometimes there's more than one. For example, I'm gonna move that. Any question on that before we go on? The function may, in fact, have several places. So let's say here's our a, f of a, and here's our b, f of b. So all it says is that it has to be continuous, right? So it could do a whole bunch of loops as it goes from one point to the other. So let's say that the value I choose is right here. So is there a value? There's 1. There's 2. There's 3 different values. Right? I can pick 3 different x values and plug those 3 different x values into the function, and they give me that same y value, whatever that is. So that could be C1, C2, and C3. Now, what does the theorem guarantee? 1. Guarantees 1 value, right? There has to be 1, but sometimes there's more than 1. Okay, let's do an example problem with the intermediate value theorem. Have you seen this before? Intermediate value theorem? A lot of times it's in like an advanced math type course or a pre-calculus course. Show that there is a root of this function somewhere in the interval from 1 to 2. And obviously we just did the intermediate value theorem. That's what we need to use for our fuel here for this particular fire. Now, a root, what's that mean? A root of a function. A 0, okay, so a root or 0 means that the function itself is 0, right? Somewhere between 1 and 2. Well, let's just see, what is the f of 1? What do you get when you put 1 into this function? 1 minus the square root of 2? Is that right? Positive or negative answer?
Positive.
1 minus the square root of 2. What's the square root of 2?
1.
Larger than 1, right? So we've got 1 minus something that's larger than 1. So if you did that, that'd be what? Approximately something like that, right? 1 minus the square root of 2. What's the f of 2?
4. 4 minus 5.
4 minus square root of 3.
Mm-hmm.
What's that approximately? Square root of 3 is what? 1.732? What's 4 minus 1.732?
2.37.
2 point.
267.
Okay, that's all the ammunition you need. Why does there have to be a root of this function somewhere between 1 and 2?
Because it passes through 0.
It's less than 0.
Okay, one of them, the f of 1 is less than 0. The f of 2 is larger than 0. And what's the other piece of ammunition that we need?
Has to be between two.
It's got to be continuous, right? And if it's continuous, don't I have to connect this dot from 1, whatever, this negative number, to 2 positive number? Don't I have to connect those somehow? Right? And if I connect them, and one's negative and one's positive, what had to happen?
It's going to take off.
Somewhere it had to take on the value 0. So somewhere between 1 and 2, we don't know exactly where, but that's not our task here. The task is there a root between 1 and 2? Absolutely there is. The f of 1 is negative, the f of 2 is positive. If it's continuous, therefore the f of some number between 1 and 2 must be 0, right? By the intermediate value. I'm looking back over my notes here. Here's an example that I missed. Let me go back to it. It's a pretty good one. This is about composed functions. Can you see the two functions that are composed to get this function? One of them would be just 1 plus the sine of x, and the other one would just be the natural log, right? So there's two functions outlined here. Now that theorem said basically the composition of composed functions is also, if they're continuous, so is the composed function. Got to be a little careful with that because we got to look at values in the domain. So let's look at, first of all, let's look at inside of here, the thing that we're taking the natural log of, 1 plus sine of x. Are there any values that if that's all we were looking at, 1 plus sine of x, is that continuous everywhere? That's continuous, right? Just be a sine graph lifted up 1 unit. But because we're taking the natural log of that result, do we have to be a little careful?
Has to be greater
Yes,
than 0.
because if we take the natural log of something, what must be true about that something?
Greater than 0.
Greater than 0,
Mm-hmm.
right? So even though 1 plus sine of x is continuous everywhere, we only want a small portion of that. We only want where 1 plus sine of x is greater than 0. Where would that be?
Between 0 and pi?
Let's look at 1 plus sine of x. Sine of x by itself looks like this, right?
Same thing.
What are we going to do with that? Lift it up 1,
Yeah.
right? So we take every point. So are we okay? Will 1 plus sine of x always be greater than 0?
Well, I mean, it's equal to 0.
It's equal to 0. Isn't that a problem, though? Can we take the natural log of 0? Can't take the natural log of 0. So we've got to be careful there. Apparently, we'd want to leave that value out, right? And how often? So what is that, 3 pi over 2? At 3 pi over 2, that's where the sine is -1. We don't want the sign to be -1 because 1 plus -1 would be 0, and then that'd force us to take the natural log of 0. We can't do that. So when again is the sign -1? I'm sorry. When is 1 plus sine of x 0 or the sine of x -1? Same issue. 2 pi later? Is that right? So we could draw this graph and it would do the same thing, right? And this interval right here would be 2 pi. So we've got some problem x's in this particular continuity issue. We would certainly have to leave these values out of the domain of the composed function. And as long as we stay away from them, picture perfect, right? We can talk about continuous. It's continuous everywhere except these values. They are not in the domain of this composed function. Okay, I had, Lisa brought up one question, but did we get that answered before class?
Yeah.
27. Just give me an idea today of how many problems, how many questions from the textbook in section 2.3. Give me an idea so I can plan a little bit. Is there mass confusion from using these limit theorems? Page 117, 118. Anybody have any issues with any of these problems?
Number 4.
Number 4, 12.
If we could get the answers to the even ones, we can
Okay.
check to see if we were right.
All right, possibly 8.
18.
All right, so I do need to plan some time to go through some of these problems. All right, that helps me out. All right, well, that'll finish us with continuity. Let me put the problems up here that I think would be to your advantage to look at, and I'll carve out some time next time we're here to go through some of those homework questions. So this is at the conclusion of 2.4, page 128, 3, 6, 7, 10, 15, 16, 18, 20, 21, 29, 33, 35, 37. About half of these are look at the problem, write down the answer, and half of them will take a significant amount of work to get to. We're not meeting tomorrow, but this homework will be due on Wednesday.
So are you taking it up?
No.
I didn't hear him say he had time.